Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to a quantity called inductance. Let me write that down. Inductance, what is it, is the million-dollar question. So what we're looking at here is we have a nice simple circuit here. We have some sort of voltage source. It's got a voltage that I labeled E for EMF. For those of you who have me in class, you know I can't stand that term EMF, but I'll use it from time to time because other books use the term EMF from time to time. But again, the important thing, that's a voltage measured in volts. This circuit has a resistance to it and a switch. And we're going to imagine now here when the switch is closed, and I'm going to just sketch a quick little graph over here to the side. And the graph here that I want to talk about is current against time. Now, if this were in the lab and we were graphing current against time, and if this were like a 12-volt source and this were a 3-ohm resistor, it's not too hard to say that, oh, the current's going to be basically 4 amps. So we might come over here and say, oh, 4 amps, and say that that current is constant. But in truth, the current doesn't get from 0 to 4 amps truly instantaneously. So this is not really a good representation of this graph. It might get there pretty fast, but not truly in a time of 0. That graph might look more something like this. Now, for the sake of this discussion, this is the time frame here that we're going to be talking about, that delta t there, the small time while the current is climbing from 0 to its maximum value of 4 amps. I should put units on this graph, 4 amps in this case. So we're going to be talking about what's happening in this time. So imagine the switch is closed. We're going to have now a clockwise current in the circuit based on the polarity of that battery. So I'm going to go ahead and draw that current right here. And it's important to realize that at least on this short time frame, that current's time dependent. Now, we're going to think about this current for a minute and remember that anytime you have a current, that current's going to create a magnetic field. The field lines around this current are circular, and you tell which way by right-hand rule. So, I might draw them maybe something like this. Now, it's important to realize that these field lines are pointing something like so. It's a two-dimensional picture. It's kind of hard to draw. But in a standard X, Y, Z coordinate system, the magnetic field direction, if I'm in the plane here of this circuit, right at this point, would be in the minus K direction. Very important that everybody, if you're watching this video, that you understand that. The field lines around these wires are circular. Let me kind of blow this up. Imagine the wire. Let me give it some thickness to it, basically. And here's our current, I. And the field lines around wires are circular, so that would look maybe something like this. You tell which way by right-hand rule. So you just kind of mentally grab that wire, thumb in the direction of the current, so the field lines would point that way. Up here, that would be, if I'm in the plane here, that would be in the minus K direction. All right. So we have magnetic fields now. In the interior of the loop, those magnetic fields are all this way, all of them. No matter where you grab that wire and you look around in that loop, you'll come to the conclusion that the field lines are in this direction. Now, the magnetic field is not going to be the same here, 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 but the directions are all going to be minus K if this circuit is kind of in the plane. Now, because we have magnetic fields now, we also have magnetic flux because we have an area here, this area right there, where there's a magnetic field vector. Remember, magnetic flux is basically field strength times area. So we have a magnetic flux through that area. Now we have to kind of come to some realization here. This flux is a function of the magnetic field at all points. Now the magnetic field's not the same everywhere, but I'll just say for now it's a function of the magnetic field strength. But remember that the magnetic field depends on I. So in essence now, the flux is a function of the current. and the flux is changing. So because we have a changing flux, we know that there's going to be a voltage induced in that loop. That's Faraday's law of induction. So depending on which of my classes you're in, Faraday's law of induction is written a couple different ways. I'm going to write it kind of in an algebraic sense first. Induced EMF is equal to the time rate of change of magnetic flux. My shorthand for that, time rate of change of magnetic flux. So it's equal to change in flux over change in time. Or in the language of calculus, the induced EMF is d phi dt. That's what change in flux over change in time would be. Now, keep in mind that this would be like per loop. If there were n loops, you'd put an n in front of each of these, but that's not important for this discussion. So we've got an induced EMF in this loop. Okay, now let's talk polarity of the induced EMF. The polarity of the induced EMF is governed by Lenz's law. Remember, nature hates a change in flux. The induced EMF will always set up a current that opposes the change in flux. In this example, the magnetic fields are all in the minus k direction, and they are increasing in strength because the field is a function of I, and I is increasing. Therefore, B is increasing, therefore the flux is increasing. To oppose the change in flux, the induced magnetic fields need to be this way, like ATUS. I can draw that better. Right, so that's the direction of the induced magnetic fields. And in order to get an induced magnetic field in that direction, you would need a current in the opposite direction. So the current, the induced current, we would say, is in the clockwise direction. Just kind of mentally grab the wire here, thumb with in the direction of that current to get a magnetic field this way. So the polarity of the induced EMF, if I were to draw it here like a battery symbol or put a voltage symbol, it doesn't matter where, but the polarity would look like this. So the induced voltage basically fights the input voltage. Now, by Faraday's law of induction, whether we look at either of these, we've got, all right, that the induced voltage is the rate that the flux changes. But the flux depends on the magnetic field, and the magnetic field depends on I. Therefore, the induced voltage must be proportional to the change in current over change in time. Or in the language of calculus, we would say the induced voltage is proportional to di dt. The proportionality constant, I'm going to put an L here, it's the same in either of these, regardless of how you're looking at it. The proportionality constant is called the inductance. If we look at what the inductance is, basically it's what has units of volt second per amp, and what it describes is this. It describes how difficult it is to change the current in the circuit. So that's how I like to define inductance. Inductance is defined as resistance to changes in current. When a circuit has a high inductance, it's very difficult to change its current. When a circuit has a very low inductance, it's really easy to change its current. Right? So you can even see that basically from this equation here. If you solve this for L, you get voltage over change, or I'm sorry, if you put the L over on the left or down here, you get that change in current over change in time would equal E over L. The larger L is, the smaller this ratio is, meaning that it's very difficult to change the current. So that's what inductance is. It's resistance to changes in current. In mechanical problems, it's analogous to mass. When an object's very massive, it's very difficult to change its velocity, or it has a lot of inertia. So, a semi-truck has a lot of mass, but a ping pong ball has a very small mass. You biff a ping pong ball, you can change its velocity easily. You biff a semi-truck, almost nothing happens. Well, inductance is similar in that if a circuit has a lot of inductance, it's very difficult to change the current. Now, I'm going to talk about how you get a lot of inductance here in a minute, but before I do that, I want to go and look at this graph over here. So graphically, here's how the inductance would affect this graph. If this circuit had an extremely high inductance, it would take a long time for the current to get to that 4 amps. This might be, maybe something like this. If the circuit has a very, very small inductance, it would get to that 4 amps really fast, maybe like this. And then that first graph I drew is, somewhere in between them. So in these curves, this would be the lowest inductance graph. This would be the next lowest, right? This would be quite a bit higher inductance. And if the circuit had a really high inductance, it would take a long, long, long time for the current to hit that 4 amps. So big things here. What is inductance? It's resistance to changes in current. What are its units? Volt second per amp. Where is it used in calculations? Well, these equations right here. Voltage across an inductor equals L delta I over delta T. Or in the language of calculus, the voltage or the EMF here across an inductor is equal to L di dt. So what I'm going to do here is get rid of some of this stuff and talk about how would you get a high inductance. So let me get rid of this. All right, so I'll get rid of those too. We'll leave this stuff. All right, well, you got to go back to think about where it came from. In this original problem, we imagined the switch closed. Then we said, all right, we've got a current now, which was time dependent, but that current created magnetic fields and hence magnetic flux through this region. And then the inductance has to do with this, what's sometimes called back voltage. Right? This is the voltage induced from the changing magnetic flux here. So induction or inductance is coming from Faraday's law of induction. So it's related to flux. Right? The inductance of a circuit is related to flux. Now, if we think about cases where we would have lots of flux or very large flux, well, let me draw one real quick here. If you're in my physics class, you've seen lots of these already. But solenoids would have a very high inductance. So I'm going to draw one here real quick. And I'm going to draw one with it. It doesn't have to have an iron core, but I'm going to draw one with an iron core because it just helps with the pictures. All right, so imagine like a chunk of iron here. And I like to give these some color here. All right, and now imagine that this has many thousands of wires wrapped around it. Now I'm not going to draw many thousands. I'm just going to draw, some. That's probably enough. All right. So devices like this, right, have a high inductance, and the reason because again, inductance is linked to flux, changes in magnetic flux within the circuit itself, and because this has many, many loops, when you run a current, for example, if I put a current in this direction. Now we're going to have magnetic fields in the interior of this iron core that are going to point this way. Now it's important that everybody understand where I'm getting those from. If you have no idea, go back and review my video on magnetic fields around wires or in solenoids. But if the current's in this direction, that means like if I pick a spot like right here, the current's this way. And the field lines around those currents are circular. And you tell which way by right-hand rule. And in the interior of this solenoid here, that would be to the left. So when we run a current here, we get lots of magnetic flux through here because there are many, 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 many loops. So this device, although it's sometimes called a solenoid, it's also called an inductor. Right? Because it's a device where you get lots and lots and lots of magnetic flux when you have a current. Right? Math-wise, like what will we be doing with inductors? Well, usually we have to talk about how they affect circuits. So one of the important things we're going to be doing is calculating or looking at circuits that have inductors, and anytime you have a circuit element or something in a circuit, and you want to write a Kirchhoff's equation for it, you have to know the voltage across it. So, some quick examples. One of the first things we talk about in circuits is the resistor, R, and the voltage across it, IR. Then we talk about capacitors. Has a capacitance C. The voltage across a capacitor is Q over C. Now we have a third one here called an inductor. Here's the circuit symbol for the inductor. It has an inductance L, and the voltage across it is equal to L, the inductance, times change in current over change in time. Or, if you prefer in the language of calculus, the voltage across an inductor is equal to L di dt. Right? So we need these voltage terms to write Kirchhoff's equations when inductors are involved. So I hope this video helps demonstrate what inductance is. Again, it's resistance to changes in current, what its units are, why you get it. You get it because of a changing magnetic flux through the circuit. What situations you'd have a high inductance? Well, when you have lots of flux. So this would be an example here of where you would have a lot of flux. How to calculate the voltage across an inductor. The voltage across an inductor is L delta I over delta T, or L equals di dt. I think I'm going to stop this video now. Have a great day.